And the first speaker will be Henriette Elvang, who will speak about an overview of progress on scattering amplitudes.
Thank you. So I'd like to thank the organizers for the opportunity to speak here, and also for the very warm welcome they've given me back here. So I've been given the task of giving an overview of amplitudes, and that's a terrifying job. But let's just start. So the idea is that we want to understand what happens when we collide particles and scatter them. This is roughly what it looks like. My job will be to try to review some of the formal aspects of the program of studying scattering amplitudes. How do you efficiently calculate scattering processes, and what are the properties of the amplitudes? So just to clarify, this is supposed to illustrate the scattering process, not the amplitude conferences. Good, so let's start from the basics. What is the motivation for this? If I calculate a scattering amplitudes involving n gluons, then the number of diagrams grow very quickly as I go up in n. These diagrams that are listed here are the so-called color-ordered diagrams. So think of these as a certain ordering of vertex operators on the rim of a disk. And this is the partial amplitude that you get out. This is the number of Feynman diagrams you need in field theory for these processes. Furthermore, the complexity of each of these diagrams is increasing as you go up. Nonetheless, it turns out that the sum of the diagrams end up being extremely simple. It's just this one-term expression, at least for the case where two of the gluons have negative helicity and the rest positive. So it's this simple ratio, a single one-term expression, expressed in spinor helicity formalism. Now, I'm not going to use that much spinor helicity formalism, so let me not go into details about it. So the questions that come up naturally are, well, given that Feynman diagrams are so complicated, why is the answer so simple? Is there a better way to calculate it? There better be, since the answer is so simple. And furthermore, does this all lead us to some new formulation of the problem of scattering amplitudes? So for the overview here, most of what I'll say has to do with n equals 4 Super-Yang-Mills in 4 dimensions, and more specialized even will be working at the origin of moduli space where all the states are massless, and even further specialized will be working basically almost all the time in the planar limit of that theory. There is, of course, other interesting aspects of n equals 4. It has a Coulomb branch where some of the states are massive. And of course, we also keep in mind that what we're really interested in eventually is also being able to express and calculate efficiently and understand scattering amplitudes in other theories, in particular QCD, maybe supersymmetric versions of QCD, possibly other theories that come up. And so I'll organize these theories basically as non-gravitational and the ones where you include gravity. So my outline is essentially that I'll spend maybe 80% of the talk in the planar limit of n equals 4. Then I'll have a little bit about the massive amplitudes on the Coulomb branch. Then I'll have even less about other theories, but I have something to say. And given that we had 2 talks yesterday about gravitational amplitudes, Johansson's talk on BCJ relations, and Bizet's talk about n equals 8, I'll say very little about amplitudes and gravity at the end. So that's the plan. So let me just view here a picture of different ways you can make your life more complicated. When you go up in the number of particles, the scattering amplitudes get increasingly complicated. Naturally, when you go up in loop level, they become increasingly complicated. And also, there's this characterization of the amplitudes the next to MHV level. And let me just remind you that MHV means maximally helicity violating. It's the sector of amplitudes that include the ones with 2 negative helicity gluons and the rest positive, namely the ones with this one-term expression I showed you before. Then if you flip one positive helicity to negative helicity, we call it next to MHV, and so on and so forth. General n to the k MHV amplitudes have 2k, k plus 2 negative helicities, and the rest positive. And that's the whole entire sector of those amplitudes, related in the n equals 4 theory, all by supersymmetry, within each sector. So you can only go up until you reach the sort of anti-MHV version of the MHV amplitude, and the maximally complicated ones are sort of the ones here, sort of in the middle of where you can reach with k. And so if you go out in all directions here at the same time, large N, higher loop level, N to the K MHV, then the problem really gets hard. So I'll start, in fact, in the plane at 0 loop level, in n equals 4 super Yang-Mills, and then move up to discuss loop amplitudes in the planar theory. Good. So the first thing we noticed was that there got to be better ways to calculate, and such methods were developed around 2004, 2005. And one goes under the name of BCFW recursion relations. The idea here is to recycle on-shell amplitudes at lower point into on-shell amplitudes at higher points. There's also another expansion, which is known as the CSW expansion, or MHV vertex expansion. And that's not really directly recursive in nature as BCFW, but it recycles the very simplest amplitudes, the ones from the MHV sector, into calculating the tree amplitudes in all the other n to the k MHV sectors. Now, both of these methods can be derived from complex analysis in a way that you've probably seen before. You take momenta and you shift them into the complex plane by some parameter c. And you do it in such a way that the momenta stay on shell and you preserve the momentum conservation. Then the amplitude is a complex function of z. Since it's a tree-level amplitude, it only has simple poles. You surround those simple poles by a contour, and provided that there's no term at infinity, no pole at infinity, then this contour integral vanishes. In other words, you can express the sum of all the residues as 0. But in particular, the residue at 0 is the actual amplitude you want when there's no shift, and that then can be expressed in terms of all the other residues. Now, the amplitudes will factorize on the simple poles, and so you get this factorization that each residues give you a factorization into a left and a right on-shell subamplitude. And this is really what is underlying these recursion relations. Directly, you get BCFW by taking a 2-line shift, and CSW you can obtain by other type multi-line shifts, but then you have to solve the recursion relation to actually get these CSW expressions. Now the question that comes up is, when are these recursion relations valid? And all you need is really this part here that you don't have the pole term at infinity. So when is such a shift good? Well, this depends on the helicities of the particles, and when we work in a theory like n equals 4 super Yang-Mills, well, we have 16 massless states, and so it's really relevant to be able to not having to distinguish between which one is which all the time, and simply have a more democratic approach to the amplitudes, to the external states. And so this is what supersymmetry helps us do. So it's natural to group the states of the n equals 4 super Yang-Mills theory into something that we could call a superfield or a super wave function, where the lowest component is the positive helicity gluon, the highest is the negative helicity gluon, and you have the gluinos here and the 6 scalars there. And this is done in terms of an auxiliary Grassmann variable, eta. Now you can regard the amplitude as a function of these you can think of them as a function of these super wave functions, and that means that the amplitude itself becomes a polynomial, and for the MHV sector, it's a very simple polynomial. It's simply just a Grassmann delta function. This was already seen in the 80s by Nair. Now, if I want a specific amplitude projected out, I simply just project out the states I want for each of the external super wave function, and that picks up the actual component amplitude that I might be interested in. Beyond the MHV level, one can write the full amplitudes as an MHV factor times polynomial of increasing Grassmann degrees, where the Grassmann degree is 4k for the n to the k sector. Now, maybe as a side remark, let me notice that the supersymmetric water densities are simply the statement that the supercharges annihilate the superamplitudes. And you can actually go ahead in the maximally supersymmetric theories and solve these water densities. But let's see where we came from. We wanted to know something about when there was a boundary term, when the shift was good. How does this help us? Well, it helps us in that we can promote the BCFW shift to a super shift. And now the delta function, the Grassmann delta function that sits here, is invariant under that shift, and only things in the denominator might shift. And that way, all the shifts are actually good. And this extends to all to the n to the k amplitudes. Moreover, not only are these recursion relations valid for all tree-level amplitudes in n equals 4 super Yang-Mills, you can actually also solve them, which was done by Drummond and Henn just a couple of years ago. And you find closed form expressions for all n to the k tree-level amplitudes in the theory. They're expressed now just here schematically as sums over R invariance, and you have to multiply that by this NMHV factor. So each of these functions here is a sum over something called R invariance, and I'll mention very shortly what invariance refers to. So tree level is solved in n equals 4 super-Yang-Mills. Now, let me just mention that there's also an alternative form of these superamplitudes in n equals 4, and that is you can promote CSW expansion to a superamplitude expression, and that allows you to get a completely different form of all the different tree-level superamplitudes. So you might be puzzled, why are there these different forms of the amplitude? Well, actually, this is something that might have a geometric interpretation, and that's one of the things I'm going to come to. The first thing I want to notice is this invariance. What does it refer to? Well, there's a new symmetry, and we can see this by introducing something called region variables. Now, tree-level amplitudes are always planar, so if I organize my external loop momenta in a certain order here, then I can label the regions between these lines, momentum lines, by variables x, I, in such a way that I declare that the momentum that separates two regions is given by the difference of the corresponding x variables. This is very nice. It makes momentum conservation automatic, because if I sum over all the momentum, this sum simply just telescopes and collapses down to 0. In these variables, there's a new symmetry, namely a sort of dual conformal or dual superconformal symmetry. And the way it works is that it acts on these region variables the same way as ordinary conformal transformations act on position space. For example, under inversion, one of these x vectors will simply be inverted the usual way. And the spinor brackets I showed in the terms of the amplitude did also transform in a simple way, provided that the two lines that go in are adjacent. If they're not adjacent, it doesn't transform in a nice way at all. So as a consequence, it turns out that the split helicity amplitudes, where all the gluons with negative helicity sit adjacently and the positive helicity sit by themselves also, these transform covariantly under dual conformal transformations. But the split helicity amplitudes, the ones where the minuses and pluses are mixed, they don't transform nicely, as you can see from this simple Park-Taylor formula, where if there's, for example, a negative helicity gluons on line 1 and 3, you would have a 1,3 angle bracket to the 4th here in the numerator, and that doesn't transform covariantly. However, when you promote the dual conformal symmetry to a superconformal symmetry, dual superconformal symmetry, and you group the amplitudes into the superamplitudes we just saw, then all the tree-level amplitudes, all the tree-level superamplitudes in n equals 4 super-Yang-Mills are dual superconformal covariant. In particular, these R invariants that I denoted before here, they are invariant because the tree-level NMHV factor that sits out in front carries the whole covariance. Now, historically, this dual conformal symmetry first showed up, there were hints of it in the perturbative calculations at loop level, and then it was really observed in Alde and Maldaceno's work at the strong coupling level. And now we've seen that it's also there at tree level in n equals 4 super-Yang-Mills. So the planar theory of n equals 4 super-Yang-Mills has the ordinary superconformal symmetry, it has the dual superconformal symmetry, and these together comprise the first two levels of a Yangian algebra. This, of course, is closely connected to the fact that the planar n equals 4 super-Yang-Mills theory is integrable. Now, let me come back to what variables we describe the amplitudes in. The spinor helicity formalism is very nice, because when you write things in terms of angle and square brackets, this means directly that the corresponding momentum is on shell null. On the other hand, the region variables we saw are nice because they make the momentum conservation manifest. But on the other hand, you can't choose these xi variables freely because the adjacent ones have to be null separated because they were the momentum which had to be null. So wouldn't it be nice to be able to have some unconstrained variables where momentum conservation is manifest, where the null condition, the null on-shellness condition is manifest, and at the same time, the dual conformal symmetry is also a clear property. This is exactly what the momentum twisters that Hodges introduced a couple of years do. So I've introduced to you the region variables, the xi, and now you map, just as like you would map from position space to twistor space, a point maps to a line. Now you map a region variable to a momentum twistor, which is a line here in momentum twistor space. And it turns out that the condition that adjacent region variables are null separated turns exactly into the statement that the two lines they correspond to in momentum twistor space intersect. And so we have a set of lines that intersect, and we now denote the intersection points as W's, and these will be the momentum twistors. Now there are 4 component objects. You can actually contract them with a 4-index tensor and define a 4 bracket that appears here. Now I don't show this, I didn't show this property of the intersection points, but it turns out that now you can choose your momentum twistors freely in projective space, and then you automatically just have the fact that you can then draw lines between them. These lines map back to the momentum region variables, which would map back to your momenta. So you can go back and forth between the variables this way. Now this 4 bracket is a very useful construct. It turns up into the R invariant. So now I'm going to give you an explicit expression, at least at the NMHV level, for these R invariants that show up in the tree-level amplitudes. The R invariants at that level depend on 3 lines, like 3 momenta, N, 1, and J, and are given in terms of this phi bracket now. And this phi bracket is described in terms of the 4 brackets. So there's a cyclic product here of 4 brackets that we defined in terms of the momentum twistors. And up here is a Grassmann delta function, which also involve the 4 brackets, as well as some momentum twister Grassmann variables that show up. Okay, in this language then, the NMHV tree amplitudes can all be written in the form where there's an MHV factor, and then there's just a simple sum over these 5 brackets here. Now I left a star here to be determined, and you can choose this in different ways. If you choose the star index here to be one of the external lines, now remember that the external lines in momentum twistor space are encoded in these n points where the different lines intersect. If I choose one of these points to sit here, then I exactly get the super BCFW representation of the amplitude. On the other hand, if I were to choose some random reference momentum twister, which doesn't have anything to do with the n external lines, then I get a CSW form of the superamplitude. So now we see some way of actually uniting these expressions, something that was not at all visible for the earlier derivations in just spinor helicity formalism. Now, it gets even better, because there's a proposal that you can interpret the amplitudes in terms of geometry. The proposal says that the amplitude should really be thought of as volumes or polytopes. And the different ways, when you calculate the volume of these polytopes, you have to triangulate them somehow. And of course, you can do that in many different ways. And the proposal of Hodges and Akani Hamed and collaborators is that the different triangulations correspond to different representations of the amplitudes. One could be BCFW representation, another BCFW representation can come out, the CSW representations, and there are even new representations for the amplitudes coming out of this. They illustrated these ideas at tree-level NMHV, and also at the one-loop MHV integrand, which is something we'll talk about a little later. Now here I'll just give you a baby example, because that's what I can handle, and to just illustrate the ideas without really showing anything. So we'll restrict to the case of, instead of CP3, we'll consider CP2. And instead of having invariants that depend on 5 labels, we have some that depend on just 3. Now, just like the amplitude here was a sum over these 5 label invariants, now we'll denote what we will call an amplitude as the sum over these 3 label invariants. And there's, again, some choice we can make for the star index. And for example, if I choose it to be 2 and want this to be a 4-point example, then, well, this is fixed to be 2. The other indices are not allowed to be 2 then, and so there are just 2 options. I can have the bracket 2, 3, 4 and 2, 4, 1. Well, it turns out, and I'm not going to show you this, but it turns out that you can interpret this 3 bracket as the area of a triangle in dual space. So you define some dual coordinates, so basically each of the labels of the triangle here each of the momentum twistors get labeled as a line here, and these 3 lines bound a triangle, and the area of that triangle is expressed as that 3 bracket. Now, if I want to calculate an amplitude at 4 point, then it depends on 4 momentum twistors, and so I will end up having 4 lines. These 4 lines will bound a region, and the claim is that the area of this region is going to be this amplitude, exactly. So how can you calculate it? Well, when we extend the lines that bound the region, we could use one of these points for the triangulation, for instance, the top point here. And so we see that if I follow the labels of the lines, then this big triangle is labeled by line 2. So 2 appears here, line 3 appears here, and line 4 appears. Whereas the smaller triangle, which we have to subtract to actually get the area of this square type region, well, that is bounded by, on one hand, line 2, on line 1, and line 4 on this side. And so putting them in the same order as I had up here, I actually have to use the antisymmetric properties of these brackets, and I end up with exactly the sum I claimed. You could see I could also have used a different triangulation. I could have used this point instead, and now the line 3 would have shown up in the areas of both the big triangle and the small triangle, so this would correspond to choosing star equal to 3. Of course, I haven't really proven anything for you here, but I'm just trying to illustrate the ideas in this simplest example. And once you actually go to the real CP3 versions of this, then, of course, it gets much more complicated, and you have to be able to chop and triangulate these polytopes in different ways. And I'll simply not show that. So tree amplitudes are fascinating. They display a lot of structure. They may even have this nice geometric interpretation. But what about loop amplitudes? Well, there are 2 aspects of loop amplitudes. One is the level of the integrand before you integrate, and then there's, of course, the integrated result. And here I'm going to proceed in non-historical order and simply start with the integrand. So remember that when we derived these tree-level recursion relations, it was key to these derivations that the functions that we were looking at were just rational functions with just simple poles. For a loop amplitude, well, loop amplitudes contain logs and polylogs and worse, and they have a much more complicated structure, and clearly don't display this simple structure that we had at the tree level. And worse, you also have to regulate the IR divergences, if there are any. But in the planar limit, we can actually keep the concept of the integrand as a well-defined object. You need the planar limit here in order to not be able to get confused about what we actually mean by the loop momentum, since that can be shifted around. So at the planar limit, the loop integrand is well-defined, and moreover, it's of course a rational function. So what are we waiting for? We should just recurse it. And if you do this, you'll find that there are pieces that contribute in these recursion relations that are much like the usual BCFW factorization pieces. They're pieces that involve lower loop level, lower point, and lower n to the k level, well, satisfying these relations, and this allows you to recurse. But there's also a new term, which is also recursible, which essentially involve a forward limit. So if you take an amplitude with one loop level lower than what you want to calculate, but then you take 2 of the adjacent external legs and just sort of glue them together and integrate over it, then you have this forward limit of the amplitude appearing. Now, generally, this forward limit is not well defined in a generic theory, but it turns out for the supersymmetric theory, as was shown by Simon Caron-Witt, then these actually are well defined, and so in particular in n equals 4, this is a well-defined limit and a well-defined construction that you can use. So there are various examples of integrands that have been obtained. For instance, well, let me just say that one loop is too simple, so we don't even worry about it. So we go to 2-loop level MHV. That has been worked out. 7.2-loop NMHV integrands were worked out, and 5.3-loop MHV integrands have been worked out. And all these come out manifestly Yangian invariant. The question is, of course, once you have obtained this integrand, how do you integrate it? But keep in mind also that if you were to obtain this integrand from Feynman diagrams, it would be an almost perhaps impossible task for something like a 7.2-loop NMHV case. So this is definitely progress, but how do you actually integrate these expressions? Well, in n equals 4 super-Yang-Mills, you need to worry about the IR divergences. The typical thing to do is to use dimensional regularization, but that breaks the dual conformal symmetry. So it's been pointed out by Hen and collaborators that you can go on the Coulomb branch and use the masses you get there to regulate the amplitudes. And the nice thing about that is that then the dual superconformal symmetry is restored, provided that you generalize it such that it also acts on the masses of the particles. Now, this is quite natural, actually, because you can obtain the Coulomb branch amplitudes. They're closely related to the higher dimensional super-Yang-Mills planar amplitudes. And they have been shown to have a dual superconformal symmetry. And so basically, the masses you see in the 4-dimensional Coulomb branch are just the extra components of the momenta in higher dimensions. And so therefore, given that they transform in higher dimensions, they will also transform the masses from the 4-dimensional point of view. Now, this is apparently a good way to proceed, but you still need to be able to perform the integrals. There's been various interesting forms of the integrands obtained, which possibly make the integration easier and the IR finite parts more manifest. And it's also been pointed out that the loop integrals you need seem to satisfy certain differential equations that give you an iterative structure that may also be very useful. But I think it's fair to say that systematics are still needed here. Certainly, integrals have been performed, for example, at 2-loop level, but we still need more systematics to really understand how to do this. So let me switch to going back in history. There is another method for obtaining loop amplitudes, which is generalized unitarity, where you exploit unitarity cuts to express the loop amplitudes in terms of the tree-level amplitudes. And this has been immensely powerful to construct higher loop amplitudes up to, for example, 4 loop level for 4-point amplitude, as well as for constructing non-planar integrands. These methods are already used to calculate QCD backgrounds, and I mean by methods, I mean both the unitarity methods as well as the recursive approaches to tree-level amplitudes. And so I'll not say more about this. Lance Dixon covered it extensively a few years ago at Strings. How much can we actually expect of loop amplitudes? Can they actually even be as simply as we hope, or is it just the tree level that is simple? Well, there's an ansatz by BDS for loop amplitudes at L-loop order in the NMHV sector, go up to any number of points, and this ansatz captures the infrared and collinear behavior of the amplitudes. But it only fixes the amplitude up to certain remainder function that can appear. Now, provided that you have the dual superconformal symmetry, this remainder function should be expressed as a function of just dual conformal cross ratios. And so, for example, one such object is a ratio here of these region variables, which are now just re-expressed in terms of the usual Mandelstam variables. Now, at 4 and 5 point, there aren't anything you can write down. Some of these objects would always, these Mandelstams would always vanish at 4 point or 5 point. So you have to go to 6 point to see anything non-trivial. And so the first non-trivial test was 6 point at 2-loop order. And a heroic effort by Del Duca, Duer, and Smirnov, a very impressive calculation, calculated this remainder function using a Wilson loop calculation. Now, after simplifying, the result was about 17 pages of various polylogs and things that are worse than polylogs, namely some Goncharov logarithms, which are defined as a set of iterative integrals. So if this was the whole story, we could lose hope that this nice structure we have seen at the tree level would not carry over to the loop level. But there's good news. If you use momentum twisters, and you use something called the symbol, which is a mathematical, sort of like a derivative type operator. You use a careful analysis of the branch Koch, and then you also apply Goncharov himself to the problem. Then this collaboration amazingly showed that the whole 17-page result reduces to a simple about 3-line expression that consists of polylogs and ordinary logarithms in various combinations of transcendentality degree 4. In fact, no Goncharov logarithms were left at the end. The result was manifestly dual conformal invariant, and I think we will hear much more about this in Anastasia's talk this afternoon. So the main message from this is that there is hope. The given that this reduces to a relatively simple expression means that we can really hope to solve the all-loop order amplitudes in n equals 4 Superamplitudes in the planar limit. There's actually been a recent paper which looks quite interesting. It suggests that instead of trying to calculate the amplitudes from Wilson loops, for example, or by other means, then you use a super Wilson loop to calculate the symbol of the amplitude. And once you have the symbol, then you can try to use Brand-Koch and perhaps also Goncharov again to try to extract the entire expression. There are some issues of how you're precisely supposed to IR regulate this, but at least it looks very promising. Okay, now why are we focusing so much on the n equals 4 planar sector? Well, it's the simplest sector we have, the one where we have the most control. So it's an excellent lab for new methods and for developing new methods. The theory is also related to QCD. It has certainly gluon scattering amplitude, though at loop level we can't just extract the information to QCD easily. We've also seen in talks that this is related through KLT, to gravity amplitude, so that's another reason why we're interested in n equals 4. And of course, it's also related to gravity via the ADS-CFT correspondence. Now, the project of solving scattering amplitudes in n equals 4 Superamplitudes just fits into a larger program where we'd also like to determine and have what we heard with Thomas' talk yesterday, solve the spectrum of scaling dimensions. There are also the problem of correlation functions and Wilson loops, and so on, form factors, and more. Now, the integrability of the planar limit played an essential role for the spectrum of solving the spectrum of scaling dimensions. We've also seen how it shows up as the Yangian structure in the amplitudes, but it hasn't played perhaps as central a role for actually extracting the information so far. It's more been a guiding principle. But there is one thing here that might actually encode this integrability much more directly, and that's the so-called Grassmannian, which might give us a dual formulation of the scattering problem. So Grassmannian, G and K, is the space of K-planes in n dimensions, and the proposal of Akane Hamed, Cachaso, Chung, and Kaplan was that this Grassmannian for n, some given n and k, knows all about the n to the k minus 2 MHV endpoint superamplitudes. So for example, the two planes should know everything about MHVs. So I just want to outline a little bit where these K-planes come from. So if we look at the momentum conservation condition and spinor helicity formalism, we can look at this. Well, each of these spinors are two-component spinors, angles and the square spinors. But we can also look at them for fixed spinor index. Then for fixed spinor index, I have for A alpha equals 1, I'll have an n-dimensional vector. Well, then I also have a second one. Those two ones for alpha 1 and 2 will define a plane in n-dimensional space. Likewise, the square spinors, they define a plane. And the momentum conservation condition is simply the statement that these two planes are going to be orthogonal to each other. Now, you can linearize this momentum conservation condition by considering all the k-planes that contain, for example, this angle plane. And then, through a series of reasoning, you're led to a certain Grassmannian integral here over the matrices here that encode the k-planes. These are some k by n matrices that show up. And in the numerator here, you have a delta function, which is effectively encoding the momentum and supermomentum conservation, but now we've gone here to twistor variables. And in the denominator, there's a set of cyclic products of minors of these C matrices. There's a normalization by the volume of GLK transformations. Now, the amazing thing about this object is that it's been argued that it encodes all the different Yangian invariants you can write. In particular, these R invariants that we've seen at the tree level. Also, it generates all the tree level amplitudes. Basically, to see that, you have to pick different contours here, and you have to pick the contours in certain ways. And once you do that, you see that the tree-level amplitudes come out, for example, in BCFW representations, or modifying this, you can get a CSW representation also. Moreover, choosing different contours, you also see different structures, and these different structures are proposed to encode all the leading singularities of the amplitudes. So these are the ones where you cut the maximal number of lines you can to fix all the momenta in the loops. So I'll refer to Nima's talk last year for further details of the Grassmannian, but this is also one of the big pieces in the puzzle of how to solve the scattering amplitudes in n equals 4 Superamplitudes in the planar limit. And this is possibly where the integrability structure may be really the most visible. Now, I mentioned that other programs, well, other directions for solving n equals 4 Superamplitudes involve correlation function and Wilson loops. But there's recently been a so-called triality proposal that correlation functions and Wilson loops and scattering amplitudes actually know something about each other, at least in certain limits. So the idea here is that, well, you have a connection between correlation functions and Wilson loops and amplitudes, but of course you have to take the locations of the correlation functions where the operators sit. They have to be null separated. The idea, well, let me just take a step back. So if I have a correlation function here of operators, then the operators sit at certain points, and the idea here is that I want these points to be identified as the momentum region variables. For me to do this, I need them to be null separated. When I make them null separated, then this object, the correlation function, will blow up. It's divergent. So I have to normalize it by some particular component. Now here, in this expression, the operators are actually supersymmetric operators in a suitable chiral superspace. And the k that I expanded in over here is just the Grassmann degree. So I normalize the correlation function by the lowest Grassmann degree, if you wish. This is the analog of the NMHV level. And then I can take the null limit. It's a finite quantity. The proposal here of this part of the triality, of this leg of the triality, is that this limit, the null limit of this ratio of correlation functions, is related to the square of the amplitude, again normalized by the NMHV level. And so if you expand this expression out, you can get a very non-trivial connection between the NMHV amplitudes and the correlation functions. And this NMHV test has been passed, and it's quite a non-trivial way that you can even try to arrange the correlation function result into something that looks like the R invariance of the NMHV amplitude. The proposal has also been generalized to the loop level, but at the level of the integrands. There's also the legs here that connect Wilson loops and amplitudes, which I'll not say more about. And as a consequence, you end up connecting the Wilson loops and the correlation functions. So there are a lot of different directions, even just for the regime of planar n equals 4 Super-Yang-Mills. We've seen the symbol. You can study basis of higher loop integrals, generalized unitarity, and so on. The whole spectrum, the Grassmannian and polytopes play a big role. And it connects nicely over to the strong coupling limit to the ADS-CFT duality. And we now also see that there's a similar proposal for triality at the weak coupling limit, at least in these null limits. There are also other theories in the world, so I'd like to proceed to those now. The first minor modification I'm going to do is to take the n equals 4 theory on the Coulomb branch. Now, going on the Coulomb branch is very useful for the IR regularization, but it's interesting in their own rights to study the massive amplitudes. Now, it's often said that when you turn on masses, then the amplitudes just get really ugly, and too bad, you have to put it on a computer. But at least in this setting here of n equals 4 Super-Yang-Mills on the Coulomb branch, we have the most controlled setting for studying amplitudes with massive states, and there's certain hope that we can get simple results. So let me just set up a specific scenario for you. We will turn on some webs for the scalars in such a way that we break the gauge group using this pattern. We'll choose to do it in a way that preserves the most asymmetry as possible. Basically, we're breaking from SO6 down to SO5. So we'll express this in terms of the SP4. Now, when we do the breaking, we split the vector fields into 2 sets of gluons under each of the gauge groups, and then W's, the strings extending between the 2 stacks of branes, are the massive ones. They're n=4 massive multiplets. In fact, we can track that the longitudinal polarization just come out as certain linear combinations of the scalar directions that we hixed. So an example of an amplitude that comes out of this is this one here. Now, it turns out when you have masses, then you are allowed to have amplitudes with just one negative helicity and the rest positive. And these now play the role of the role that the NMHV amplitudes played in the massless theory. So you have the UHV amplitudes, these ultra-helicity violating amplitudes, and it takes, for all n, it takes this form here for the case where m is the mass of the 2 first states and the rest are massless. So this is rather simple. And it's much simpler than you might have hoped by even thinking about the Feynman rules on the Coulomb branch. Now it depends on a null reference vector here, which is introduced for massive spinor helicity formalism. You just introduce a null reference vector so that you can decompose the massive momentum on 2 null directions, and that's what shows up in this expression here. You see, this is also actually at the level of a superamplitude. It's a little bit like this is a 1/4 supersymmetric, whereas the usual MHV look like 1/2. Now, think about the following. Suppose you're at the origin of moduli space and you look at some amplitude with some external scalars. If you take a soft scalar limit, you're going to probe the moduli space nearby. And so you might hope to learn something about the small mass Coulomb branch amplitudes. Now, these soft scalar limits are the same ones that Niklas talked about yesterday, the same ones that we used to study E77 and n=8 in the n=8 theory. Of course, there the soft limits had to vanish. They don't here because the Coulomb branch encodes different physics from the one from the origin. So how could you actually test this? Well, if you take a 4-point amplitude with 2 massive vectors and 2 gluons, we can calculate it, and it takes this simple form. It actually just comes out of the amplitude I showed you before. In particular, it has a massive propagator. Now, if I take the limit where the mass is much smaller than all the Mandelstam variables in the problem, then I can write this as the leading small mass result. On the other hand, if I want to try to get to this result from the origin of moduli space, then I can look at a massless amplitude, where I recognize I have 4 vector states, 1 with minus helicity and 2 with positive, and then I've inserted a pair of Bev scalars. Now, in the limit where I take the momentum of these scalars to 0, after actually symmetrizing it to get rid of collinear divergences, then I end up with exactly the same result there. So this really realizes the statement I made that I can go from soft limits from the origin of moduli space on the Coulomb branch. Now, a dream would be to see how this massive propagator actually gets resummed from the soft scalar limits. And this can actually also be realized, and that this was done in a beautiful work by Michael Kiermaier, who saw that you can express the amplitudes in such a way that you directly see how massive propagators get summed. Basically, the different orders in the mass comes from inserting extra pairs of scalars in the massless case. And you sum over all these ones in a prescribed way, and you reproduce the entire massive scattering amplitude. So this motivates also, in Michael's work, it also motivates a new proposal for a CSW type expansion for 3-level amplitudes and possibly also loop integrands at the Coulomb branch. So that's another method of now constructing these massive amplitudes. Okay. So I'm going to go now from the n=4 theory to more general theories. And, well, one of the things I'll focus on here are the 3-level recursion relations. So we saw how powerful they were and how much the work in n=4 Super-Yang-Mills was based on the 3-level recursion relations. But the question is now, if we go to more general theories, when are these recursion relations valid? So one study of this was done by Cachaso and Benincasa a couple of years ago, and they established that there was a link between the factorized form you need to derive BCFW and various classic S-matrix results. For example, that you can't have higher spin theories in flat space, that if you have an interacting spin 1 theory, it's got to be Yang-Mills, and the structure, well, and you can actually derive that the structure constants are antisymmetric, and so on. What about other types of recursion? What kind of insights might we get for when recursion relations are valid? Well, I'm going to give you a very simple example of this. So the setting for it is these all-line shifts that are possible that you can use to derive CSW expansions. So you shift all the square brackets of the external states, but not the angles. And then you can study the large C fall-off that is needed to derive the recursion relations. Now, we study this validity in general 4-dimensional Lorentz invariant theories, and we don't need supersymmetry. We can do this with both massless and massive particles. We can do it with and without non-renormalizable effective interactions. So an example of such an effective interaction that you might be interested in including could be the effective dimension 5 operator for Higgs-gluon fusion. So when you can effectively integrate out, when you have two gluons interacting with a top quark via Higgs boson via a top loop, you can integrate out the heavy top and get an effective dimension 5 operator. And these are then used actually to derive, it basically reduces the loop level by 1 when you're calculating amplitudes. So those are indeed relevant to look at. Now, we can then exploit dimensional analysis and something called little group scaling to find a sufficient condition for when these all-line shift recursion relations are valid. And it turns out to be a very simple condition just involving the number of particles, the sum of the helicities of the external particles, as well as the product, the mass dimension of the product of the coupling constants that contributes to the process. Now I should say that in the case where we're studying massive particles, what I mean by helicity is helicity in a fixed frame that I use to define these spinor helicity amplitudes. So here's the very simple example. Let me look at just scalar QED. So I have a scalar coupled to a photon. In the Lagrangian, I have two types of interactions, photon with two scalars and two photons with two scalars. Now if I look at a simple process with two negative helicity photons interacting with the scalars, I just can write down this quantity here to test the validity of the recursion relations. Now, well, it's 4 particles. The mass dimension of the coupling is 0, of course. And so the sum of the helicity is -2. So this is negative, and it means that the amplitude is constructible through these recursion relations. And so in particular, you'll notice that no information is then needed about the 4-point contact term in the Lagrangian to do this. The role of that term is to ensure the off-shell gauge invariance of the Lagrangian, and we don't need it to extract the on-shell information for the amplitude. Now, actually, this is somewhat bad example because it turns out that this particular amplitude vanishes, but you'll see it recursively by the fact that the sum of these two CSW-type diagrams you get out is actually 0, but each of the diagrams are not. Now, let me then take an amplitude in the same theory, but involving 4 external scalars. Now, I compute my S quantity here and find that it's 0, so that means that the amplitude goes as order 1 for large C. So it's certainly not constructible by these means. Well, how can that be? Well, it's not a big surprise, because how are my recursion relations supposed to know by themselves whether my theory has a lambda phi to the 4 interaction in it? This is some independent gauge invariant coupling that you have to put in by hand if you have it. And since this relation here was derived on so general grounds as just dimensional analysis and little group scaling, there's no way that, well, basically the theory can't know by hand whether I put in this coupling or not, particularly because this coupling is also dimensionless. However, if I were to calculate the scalar amplitudes starting at 5 point and higher, they would be constructible, because now I have supplied in the lower point this interaction here. So then I can construct everything above that. So the lesson is that we really need to supply the individual gauge invariant information that we want to put in, and then recursion relations can be expected, roughly speaking, to take care of the rest. Well, you might just contradict me and say, well, in n equals 4 super Yang-Mills, there is a 4-scalar interaction in the Lagrangian. So how can it be that BCFW allow us to calculate all the amplitudes there from just the 3-point vertices? And they only do that when you tell the recursion relations more about the symmetries, namely when we make them super recursion relations and also shift these Grassmann variables that go along. And in particular, that's when in n equals 4, when you saw the super BCFW recursion relations, you put that information of supersymmetry in, and then this coupling here is actually fixed by the other couplings at 3-point level, and so that's why you can recurse it. So the lesson here is that the Lagrangians can look in many different ways. You can write them, you can do field redefinitions, you can fix gauges in many different ways. But once you supply the gauge invariant information, that should be all you need to really calculate this on-shell information. So here I'm listing just a few different directions for going beyond n equals 4 super Yang-Mills. So at the tree level, we can actually get the QCD amplitude with massless quarks from the n equals 4 super Yang-Mills amplitudes. And this has been done by just simply taking a linear combination of the n equals 4 tree amplitudes. You can, of course, also do a very simple direct truncation at tree level of the n equals 4 amplitudes to pure Yang-Mills with less supersymmetry. And you can then also see that in these theories for n equals 0, 1, and 2, something is going to be different from n equals 4 because there's a running coupling. The one-loop beta function, for example, is, of course, non-vanishing. Now, you can extract information of this from what are called the bubble coefficients of the theory, and they turn out to be very simply related to the tree-level amplitudes, and the coefficient that shows up in this relationship is simply the one-loop beta function coefficient. And this is something that comes out by just doing the on-shell constructions too. Now, in a similar analysis, one might ask, when are these so-called bubbles and triangles absent? This is a property of n equals 4 super Yang-Mills and n equals 8 supergravity. And Lal and Rahu explored what are the sort of next to simplest theories in which you don't have these bubbles and triangles. And they found some interesting results that basically this reduces to a group theoretic problem. We mentioned dual conformal symmetry earlier, that has been verified in 6 and 10 dimensions. And one of the things we need here is really tools to explore the higher dimensional theories. So if this whole structure mainly relies on gauge invariance, then it certainly should also be valid in higher dimensions and in lower dimensions, and you can go ahead and explore amplitudes in other theories using these techniques. Finally, for practical applications, the tools that have been developed in n equals 4 have certainly been applied in practical applications. They are implemented and automated in numerical codes, such as Black Hat and these other programs listed here. Here I'm simply stealing a slide from Lance Dixon's QFT talk from earlier this year. And so to just give an overview of what kind of processes this is used for. Now, from this maximally practical part to the part of calculating amplitudes in gravity. Now, given that we had so much on that yesterday, I'll just have one slide where I point out some similarities and differences between the n equals 4 super Yang-Mills theory and n equals 8 supergravity. So our main difference is, of course, that we have the color ordering n equals 4. This is what allows us to get planar limits. And there's no such thing in the gravitational theories, of course. Nonetheless, super BCFW recursion relations are valid for tree amplitudes in both theories. But if you look at CSW, while valid in n equals 4, it's not in general in n equals 8. The BCJ relations we saw yesterday are very interesting new developments. The way that they occur in Yang-Mills theory would be nice to clarify and understand better, and how the squaring relations work in gravity and the underlying reason why these work would be very nice to understand better. The questions of UV properties, of course, come up in gravity. It's the n equals 4 theory is, of course, finite. The question now seems to be in n equals 8, at which loop order we find the first divergence. It certainly seems like you need more than the E7-7 symmetry, though there's some various approaches to that. Now, in the planar limit, we could define these region variables, which made the integrand well-behaved, and which made momentum conservation manifest. For gravity amplitudes and amplitudes that are non-planar, can we possibly define such variables? What are the right variables to look at for these ones? And furthermore, while we in the n=4 theory had the Yangian symmetry from dual conformal and ordinary conformal symmetry, is there any kind of extended symmetry in the gravity theories that would play the same role? Of course, it's going to be much different, in part because we don't have the planar limit, we don't have the same variables, and we certainly don't have the conformal symmetry. So something else has to happen if there is some way of realizing that. So let me end here by an amplitude, which has many legs and many directions in which progress is being made. I want to highlight that this is an area which is exciting, I think, to work in because of the formal aspect, the connections that go possibly to stringy origins of this work, but also is directly connected to physics that is relevant for the LHC and for particle physics experiments. There are many directions, as we've seen, but there are also many applications in new areas. For example, the use of spinor helicity formalism for de Sitter perturbation theory. And one lesson I think would be interesting to take from here is whether these methods of working in manifestly gauge-invariant quantities could be used in other contexts, in other areas of physics too, to help us with more efficient calculational techniques and new insights. Thank you.
So thank you very much. Comments, questions? It was a very clear talk, I can see that. Okay. Okay, Joe.
So you said that 60 and 10D have dual superconformal symmetry. They don't have superconformal symmetry.
Right.
Can you repeat the question?
Yeah, I'll repeat the question. So I mentioned that we've seen in 6 and 10 dimensions that the amplitudes have a dual superconformal symmetry, but they don't have a conformal symmetry. Of course, the couplings are dimension full. So Joe asked me to elaborate on that. So one question you might ask is if I take the n=4 theory on the Coulomb branch, this is equivalent eventually to looking at it in 6D, then could there be something left of the integrable structure? And it seems very difficult because if there was something that would play the role of the level 0, that should probably in 6 dimension correspond to this, the usual conformal, ordinary conformal symmetries. And since we don't have that, it looks very difficult to go anything like that. So I think that the special properties of the n=4 massless theory in the planar limit is not going to carry over to the other ones. But other than that, it's obvious there's no ordinary conformal symmetry in the high-dimensional theories, so I don't have much to say about that.
Okay. I don't see any other hands. So thanks once more.
Thank you.